We'll learn about a topic in Galois theory. It's called Galois Co-Homology, and one theorem we will prove. It's called Hilbert 90 or Hilbert's theorem 90. So let me begin with some general facts or definitions. Then we'll start proving theorems. And this is a new topic, and you might be thinking that why I'm certainly studying this topic. So there is no reason. I will complete full playlist of field and Galois whenever I will have time, because nowadays schedule is too hectic, so it is not possible to manage actually. So don't worry, I will completing theory as well, and field and Galois theory as well. So let me start with some new definitions. Today we'll start here about what I've said, Galois cohomology. This is Galois cohomology, and we'll prove Hilbert 90. Hilbert's 90 for any Galois extension. So there is one Hilbert 90 which is only for the cyclic Galois extensions. So today we'll learn for in general Hilbert 90 for any finite extension. So for infinite extension we don't bother till now. We'll not worry about the infinite Galois extension because there is topology is needed. So let me begin with some definition. Let's suppose you have a suppose I have a group G. Let G be a group and M be an abelian group. Okay, I'm assuming G is a finite group. Okay, G is a finite group and M must be an abelian group. M be an abelian group. We say M is a G module, or M is a G module. Whoever studied module theory, we generally define a module over a ring, right? On an arbitrary ring. Whenever we module any module over a field, then we call this is a vector space. Otherwise, if we actually define a module over any arbitrary ring, this is called actually this is actually called module. Module is the first generalization of vector spaces, because vector space we define on an arbitrary field, but here we have defined if we define any set, any structure on any kind, it is similar to vector space structure. If we want to define over arbitrary ring, then this is called a module, and here I am calling it if it's G module. If we similar action will take if there exists an action, or if there exists a map G cross M to M, and where for arbitrary module what we actually define, we define on arbitrary ring, and here we are defining on a group G. So such that if we take any sigma over here and any M1 plus M2, it should give you sigma M1 plus sigma M2, right? And remember, okay, that's fine. And if we have any sigma tau over M, suppose M, not M1, I'm defining over M, this is actually sigma tau of M. Okay, and third one is, this is second one, and third one is says that any one, if you have group element 1 and M, it should be give you M for every M, okay, inside the group M, and here for every M1 M2 M inside this M, and sigma tau inside your group, okay, G. So then we say this M is a Z module. Okay, so what actually we need to produce a cohomology group. Okay, first of all we'll produce a cohomology group. What is a cohomology group? For that we just define a new terminology, what is called one co-cycle or crossed homomorphism. So actually whenever G module, and we say, and here there is one more terminology I want to make, that is your G is group and G is an A module. Okay, so define, so G be a finite group G be a finite group. Sorry, write it as a if M be a G module, let M be a G module, and G acts on M, that is G is acting on M. Okay, if G acts on M, we can define the fixed points of G, right? We can define the fixed points of G. How do we define the fixed points of G? So actually it is defined as M upper script G. This is all those elements in M such that GM equal to M for every G inside your GM, means that G acting on M is M for every G is inside your group G. So this is called the fixed point group. Fixed points of G. I'm collecting all the fixed points. If you have started group action, I'm collecting all the fixed points of G, right? So let it define it as it is, and now we define another set. Okay, this is defined depending on the action of G, right? Okay, so now we'll define something strange. Okay, so what I'm going to define. Okay, so if you have, okay, we have G module, we have this fixed point group. Now I'm going to define a new set. This is, let us call it Z1 of GM. It is defined as I'm collecting all the functions, all the morphisms, from G to M, which satisfy certain properties, that is f of, if I apply on sigma tau, this is actually f of sigma plus sigma f of tau. Okay, this is my group. So this is, I have defined this as in such a way. This is like homomorphism, or in kind of as a kind of homomorphism. See, if G trivially acts on if G trivially acts on this, acts on M, then what can you say about this set? Can you say about this set anything? If G acts trivially on M, then this is all nothing but all homomorphisms. This is hom G M. If G acts to M trivially. Okay, so now can you see this will form a group. Suppose I have taken two elements. What is this? Suppose I have taken two elements. Okay, let F comma G, two members of this group Z GM, and what can you say about that? Means F satisfies F sigma tau equal to F of sigma plus sigma F of tau, and G of sigma tau equals to G of sigma plus sigma G of tau. What can you say about F plus G? F plus G is also satisfy this. Of course, F plus G will satisfy this. So this will form a group. Okay, this will form this Z1 GM will form a group. Will form a group, and this we call this set as we call it set of all one co-cycles in G. Okay, set of all one co-cycles in G. Now these are called one co-cycle, right? So this set, actually this is a group, actually this set is one co-cycles in G, right? Now we are defining another subset of this. So now define B 1 g m. I'm collecting all those functions from g to m such that there exists an m in m such that this f of sigma can be written as sigma of m minus m. Okay, so this is called actually this set is called one co-boundary. So this set is called, can you see that this b1 is a sub not only a subset, this is a subgroup. This b1 of gm is a subgroup of this co-boundary. Can you see? See, if you have any element over here, so any element over here, this will definitely lie in here. Can you see that? See, here the elements are look like in b1. Suppose you have taken one element from b, and what actually f of sigma tau will be? F of sigma tau and f of this is a subgroup. Okay, this is a special kind of homomorphisms. This is a special kind of, yeah, actually this is called homomorphism, and this is called one co-cycle, or this is called also crossed homomorphisms. Okay, and these are called principal crossed homomorphism. Okay, and otherwise it is called a co-boundary, one co-boundary ng, one co-boundary ng. So you can verify that this is a subset of this, and it is very easy to check. You just take one element here and you just show it here, and this will enough for a subset, and you just show that this is a closed under the operation, under the action actually. Okay, so now so this is a subgroup, and what can you say about this group? This is a abelian group, right? So this I can think of as a normal subgroup. So now I can define the quotient of it. Okay, quotient of it, our main group is gm, and quotiented by this b1 gm, and this we call it h1 gm. This is called first co-homology group. This is called first co-homology group, right? Now similarly you can define this h2 in a similar way. You can define h2 g2 z2 b2 hgm. Similarly you can define hi for any I natural number, right? So now we are not bother about this h1 hi's, I is greater than 1. So we'll only work with this h1. This is first co-homology group, and this will leads to something new theorem which is called Hilbert 90. So now, so this will form a group, right? And this h1 is actually set of all, these are set of all crossed homomorphisms or one co-cycles, and this is called set of all one co-boundaries, and okay, so now we can proceed for a theorem in the Galois theory, which is called Hilbert 90 or Hilbert's theorem 90. Sometimes it's called Hilbert 90. So what is that? Let me state the theorem first. What it says actually. Hilbert'S 90, or sometimes it's called Hilbert's theorem 90. So what it says, this is a theorem. Okay, so this is a theorem. What is actually this theorem says? Suppose you have let k over f actually, k over f be a, let us suppose k over f be a Galois extension suppose K over F. Okay, I don't know what is happening. Okay, K over F, if it is a Galois extension, now we can define about the Galois group. With Galois group, Galois group G equals to gal K over F. This is G. Okay, this is with the Galois group K over F. Now we can define this Galois group and this actually your K as see here with Galois group we can define the first cohomology group. You can definitely define the first cohomology group, right? So first cohomology group is actually first cohomology group in this group G, for this group Galois group G. Then it says that the set of all crossed homomorphisms and the set of all principal crossed homomorphisms are actually same. That means if you do then H1 of your Galois group K over F and comma your K star, that means the set of group of units of K. Okay, this is an abelian group, of course, right? K is a field, so this is actually 0. That means this is trivial group. That is set of all co-boundaries and set of all okay, that it is enough to say that the quotient group. What is the quotient? You can say this is the quotient. Okay, this is, so that means that is okay, that is Z1 of gal K over F, gal K over F over K star quotiented by first co-boundary gal K over F. Okay, gal K over F, actually here is gal K over F K star is 0. It is enough to say that these two groups are same. This is trivial. So now this is actually called first co-cycle or principal crossed homomorphism, or one co-cycles, one co-boundaries, right? So these are same. So how do we prove that? You have to say that this, see, if I want to show that these two are this is 0, then it is enough to it will what does it mean? That means you have to show that these two groups are same, then it will be done, then it will comes out to be a trivial group, right? So now before proving that, I will have to you have to know about you have to know some basic some necessary things that I will use. That is, first is called character. What is character? You have to okay, yeah, what is a character? I'll define character now. Okay, so what is character? Before proving, I will prove this theorem. Okay, I will definitely prove this theorem. That let me just define some new notion. It is called a character, the notion of character. What is character? Character of a group. Character of a group. Group character of a group or group character. What is a character? Is a, let you have a group G. Let G be a group and F be a field. A group character sigma from G to F with the unit group of F is nothing but is a character is a homomorphism. That's the definition of character. That's it. So this is called a character, GBA group and FBA field. Then now the group character is defined by the sigma. The sigma is from G to F star, and these are called group character. Okay, these are called group character. Now, when do we suppose you have the collection of characters in the group? So there are so many homomorphisms sigma i's. Suppose you have the sigma i's from G to F star. So I will use whether this, when do we say that this sigma is a linearly independent, or when we say this is linearly dependent, right? So for this concept, you have to suppose you have a character, some characters that here. Suppose sigma 1, sigma 2, sigma 1, sigma 2, sigma n are n distinct characters. N distinct characters. N distinct character. When we say this is linearly independent, on them, for this, you have to use a lemma or a proposition which is called Artin's, or sometimes it's called Dedekind. Some book is referred as an Artin linearly independency of characters, and some books are called Dedekind linearly independency of characters. So I will just simply say the linear independency of characters. Dependency of characters. Whether it will give by Artin or Dedekind. Some book refer this as an Artin linear independence of character, some book refer this as Dedekind's linear independence of character. Both are same. So how do we? So first of all, my question is, when do we say a characters are linearly independent or dependent? Suppose you have let sigma I from 1 to n be n distinct characters in G. We say sigma is, or sigma 1, sigma 2 as a set actually. We say sigma 1, sigma 2, sigma n are linearly independent if we have the summation sigma I, instead of sigma I, we just first you take ai, sigma I is 0. For if your linear combination of ai sigma is 0, this should imply that ai equals to 0 for every I from 1 to n. If for ai's inside the f star actually this happen, f star ai's here, then the summation of this happens, then all the ai's are 0, as it is the linear independence definition of linear independency. Okay, so this is called, and then we say this is linearly independent. Otherwise we call linear dependent. Otherwise linearly dependent. That means there exists at least one ai inside the field, your field, the group actually, the unit group of the field dependent. If there exists one I such that the sum is 0 but ai is not 0, non-zero, at least some ai which is non-zero. So that's the different. Okay, linear. Otherwise linearly dependent. Okay. First of all, why this is called linearly independency of characters? Why this is linear? Why the characters are always linearly independent? Suppose you have okay, so proof of the linear independency of character, the characters are linearly independent. Suppose you have sigma 1, sigma n are n distinct characters of G. N distinct characters of G, then they are linearly independent. So how do we show that? We will use induction before that. Suppose if we have 1, suppose your a1 sigma 1 is 0, so this is 0. This will this implies that a1 sigma 1 of x equals to 0 for every x in G, right? But can sigma x be 0? Sigma x cannot be 0 because sigma is from G to f star. So sigma, the image of value will be lying in f star, but f star does not have any 0, does not contain any 0. So this sigma 1 of x can never be 0. This implies that a1 has to be equals to 0, right? So for 1 we are done. What about 2 and 3 cases? We'll use induction. What is the induction hypothesis? If your k is any of 1 up to n minus 1, then the result is true. That is, for any k k belongs to 1 to up to n minus 1, sigma 1, sigma 2, sigma 1, sigma n minus 1 is Li. This is our induction step or induction hypothesis. Now you will show that this using this induction you will show that this these characters are linearly independent. You use towards a contradiction. Suppose towards a contradiction, the sigma 1, sigma 2 are not Li, not linearly independent. So you will have there exist AIs inside this F. AIs inside this F such that not all 0, but your sum AI sigma I is 0 from 1 to n. Okay. So that's your induction step. Now you just contradict something by some contradicts yourself that this can never happen. If you have AI, if your sigma AI sigma I is 0, then you have to arrive at a contradiction, right? So I'm not doing this proof. I'm giving and I have given you enough in. So you just do the simple calculation, right? So suppose AI is not 0, suppose this is 0. So if any of the AI is 0 for some I, then this will be linearly dependent. This will be linearly dependent. In fact, this will be linearly dependent with linearly dependent of characters with less than n elements. But it cannot happen because we have already assumed that this set is already linearly independent. So we cannot take this. So all the AIs are non-zero. That means all this sum is non-zero. This sum has to be non-zero. That's the actual thing. Because sigma I's can never be this sum AIs are non-zero. Okay, all the AIs, none of the AIs can be 0, because if any one of the AIs will be 0, if any one of the AI is 0, then your linearly independency will fail for this n minus 1 element. So none of them has to be 0. So now you have to define something. You have to divide by at least one AI. Suppose you have defined divide by an. If you divide this by, okay, let's do the proof. AIs are non-zero. Okay, so what it says that a1 sigma 1 plus a2 sigma 2 plus plus an sigma n is 0, but AIs are non-zero. If any of AI is equal to 0, this will imply that this will contradict, this will imply this is not linearly independent. The sigma 1 up to sigma n minus 1, n is from sigma n minus 1. Here the indexing can be varied, right? For any set of, for any k inside 1 to n minus 1 actually. Okay, this is, so this implies this is not Li, not remain Li. So this is a contradiction. So it can never happen. So any of AI, so all AI is non-zero for every I. Okay, so now you divide by an. You divide this sum by an. This sum by an, whatever the sum is here. So this is this sum by an. If we divide it by an, what will happen? Suppose I am a1 by an, I am calling it b1 sigma 1 plus b2 sigma 2 plus plus sigma n all will be there. Okay, now they are all distinct. So sigma 1 can never be equal to sigma n identically. They are distinct. Sigma 1 can never be equal to sigma n for every identically. One point wise, maybe some point identically. So this implies there exists one G inside the G such that sigma 1 of G can never be equal to sigma n of G. Okay, and your x is you have let x be an element in G, and you have already G is in. Okay, I have previously I was okay. So G is in G. Now we can now xg is a member of G. Now we can apply character on this element G, on this xg element of G. Now you apply this to xg, b1 sigma 1 of xg plus plus I'm going to first sigma n of xg is 0, xg or gx, whatever it is. So this what does it will imply? So this will be 1 sigma 1 of x sigma 1 of g plus dot 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 plus sigma n of x sigma n of x sigma n of g. Sorry. For okay, let me just a second. 40, yeah. So sigma n of g, this is 0. So sigma you divide it by sigma n of g, b1 sigma 1 of g by sigma n of g, sigma 1 of g by sigma n of g I have divided by this into sigma 1 of x plus dot 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 up to, we will define sigma n of g sigma n of x is 0, right? Now this is, suppose you have given it 1, sorry, you give it 2 and I have 1, wherever I have this is 1, suppose. Now you divide, now you just, okay, you can give it sigma n of x for every x, right? X. So now you can define whatever you call, you do 2 minus 1. If you do 2 minus 1, what you will get? You will get b1 times sigma 1 of g by sigma n of g minus 1 into sigma 1 of x plus dot 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 plus dot dot dot, this is b n minus 1 up to sigma n minus 1. I am not giving sigma n, this is actually g, this is g minus 1, okay, this is sigma n minus 1 of x is 0, right? So now if this is 0, but you know that this sigma 1 sigma up to sigma n minus 1, these are linearly independent because of the assumption whatever we have assumed. So if then the result is true, that means these are Li for any sigma 1 sigma 2, this sigma 1 up to sigma n minus 1, these are Li. But if what you got, well, that means that this implies that your bi's are 0 for every i, up to n minus 1. That means your in particular b1 is 0. This implies that b1 is 0. This is b1. This implies that no, bi, not bi's are 0, that all these are 0, sorry. Okay, so this implies that b1 times sigma 1 of g by sigma n of g minus 1, these are 0. But b1 can never be 0. b1 can, because what is b1? b1 is a1 by an. All the ai's are non-zero, so b1 has to be non-zero. So b1 can never be 0. This implies that sigma 1 of g by sigma n of g, this has to be equals to 1. This implies that sigma 1 of g has to be equals to sigma n of g. But this is a contradiction. Why this is a contradiction? What we have assumed here, sigma 1 of g is not equals to, okay, there exists g such that sigma 1 of g not equal to sigma n of g, okay. This is the contradiction to the fact this, so they have to be linearly independent, so this is a contradiction, okay. So sigma I, if they are distinct, I equal to 1 to n, are always linearly independent, okay. So now come back to our Hilbert's 90, whatever the Hilbert 90 was. So that's why the entire Hilbert 90 will prove by actually this linearly independency of character, okay. The entire Hilbert 90 will depend on this. If you have this linearly independence of character, then you can define always this proof very easily. So what it says, that what I was having the Hilbert 90, let me recall character, okay. Hilbert 90 says that if you have k over every any Galois extension with Galois group G, then H1 Galois group with K star is 0. That means your co-boundaries and co-cycles are actually same. That means your co-boundaries and co-cycles are actually precisely same. So you have to show proof Hilbert 90. I think this pen is not visible. Let me just yeah. So what you have to show actually, Z1 of G means Galois group, okay, and what is K over F or K star is actually you have to same the co-boundaries and co-cycles are same. Then we'll be done. Then we'll be done. So because you have to show that the first cohomology group of G K star is 0. That is, this implies that this Z1 G K star quotiented by B1 G K star is 0. This is enough to show this. Okay, this you have to show that the all the principal, this is called it is crossed homomorphism, crossed home, and this is called principal crossed homomorphisms. This is called crossed homomorphism. All the crossed homomorphisms are nothing but principal crossed homomorphism. That's how you have to show. Nothing else is needed. So suppose you have taken, so just you have to show, see, we are in a multiplicative group. Your K is a multiplicative group. Now you have to show if you have any F. Suppose you have F is Z1 of G K star. This means that F of sigma tau will be F of sigma into sigma action at F of tau. See, here your K star is a multiplicative group, so action should be here multiplication. Okay, so that's why we have defined this Z group as a plus, but here since this is a multiplicative group, so we cannot talk about plus, so we can definitely erase it as a plus, and we have to make it as a multiplicative group. That means that what actually it means that F of sigma F of tau. Okay, now to show there exists, if I can show there exists a beta in K star such that F of sigma, earlier it was sigma of B minus B, but now it will have, since this is a multiplicative group, a beta inverse sigma of beta. Okay, since you are in a multiplicative group, and this will be enough to show, right? So let me just start with that. So this is the actual we need to show. So let me start. So then let see here. Okay, see this B1 B upper 1 G means Galois group, okay, is already contained in Z1 G. First co-boundaries are already contained in first co-cycles, one co-cycles. We have to show that this is true, right? So now let F be an element in the first co-cycles group. That means that F of sigma tau, this is actually F of sigma plus sigma F of, since here it is multiplication, and sigma F of tau the action, right? So what can you say about now this here, right? So now from here, can you find out what is sigma F of tau? Sigma F of tau is actually equal to F of sigma inverse F of sigma tau. Are you getting this? I am keeping this side, and this I am here, this side. That's why I have taken F of sigma inverse, because F of sigma of course have inverse, because this is in K star. Okay, this K star. So this is right. Now what actually you can do is, we can do now we have to show that this element is lying inside the first co-boundary, right? So you have to show this is the first co-boundary, this is lying inside the first co-boundary. So bilinearly this f of sigmas, see this f of sigma and this tau, sorry f of tau and tau, this can be seen, this can be viewed, this of f of tau, this can be seen as a character in G, this can be viewed as a character in G. So since the characters are linearly independent, so we can must have something element for which this is non-zero, there is something which is non-zero, right? In the characters by linear data kinds or attain linearly independency of characters, so what we can say is as a character, this can be viewed as a characters. So now if I view this as a character, that means that there exists, so there exists an alpha, there exists alpha in the your field, actually sorry if k, actually my field is k, then there exists such that this summation of f of tau into tau alpha is 0, sorry this is non-zero by linearly independency of characters. This can be viewed as a character because we just now seen that the characters are always linearly independent, set of character distinct characters are linearly, see here f of sigma, f of tau and tau are from, sorry my field k to k, so we can definitely think them as a character, of course, definitely, of course, why not, because yeah so this always this can view as a character. So this is, if this is non-zero, now this non-zero element, see the tau will vary in G in your Galois group. So this is, so now how many characters are there, how many, as many distinct elements of G's are there, this is okay. Now this is non-zero, right? So now call this to be beta to be, call beta to be this f of, not actually beta actually, so you can take it as gamma, so actually as gamma, say gamma defined as something called tau inside the G, f of tau and tau of alpha, which is non-zero. So you can definitely talk about we apply sigma here, sigma of gamma, this will be, and sigma of gamma, what will that be, sigma of f of tau, sigma of f of tau will be there, and sigma of f of tau will be there, and your sigma will operate at tau, and the sigma will operate at tau, sigma will operate at tau at alpha, right? So this much I have. So now you know that sigma of gamma, this is actually summation, here tau already belongs to, sigma is a fixed, okay, I have operated only sigma, this is G, and this tau will vary in G. What is sigma of f of alpha? See here, sigma of f of tau, sigma of f of tau actually, sigma of f of sigma inverse into sigma f of sigma tau. So what is it, what it is so f of it is f of sigma inverse into f of sigma tau, I guess, right, into f of sigma tau, yeah, this is, so this is this, and you have already have sigma of tau of alpha actually, okay. Now you, since this is independent of this tau, then you can take it to be sigma of f of sigma inverse, and I will vary this tau to be here f of sigma tau, sigma of tau of alpha, right? So see here, one thing notice, sigma of gamma, so notice one thing here, sigma f of sigma inverse, but here your summation is lying, your summation is varying over all the elements of G. So you can think it as some sigma tau. Suppose your eta is in G, f of eta sigma of eta. You can think that because your sigma tau is varying over entire G. So this is it. And what is this? This is nothing but your gamma. See here, tau is here varying. It's the same thing. These things and these things is same now. So you can definitely see this as f of sigma inverse, and this is your gamma, right? So you just pull it back here. F of sigma is here, then f of sigma will be just I have pulled back your f of sigma here, and this I have taken to be here. So what will that be? Sigma by sigma of gamma sigma of gamma inverse. That's it. Now your gamma to be, you choose your gamma to be beta inverse. That will be enough. See, your f of sigma is actually gamma sigma of gamma inverse gamma. Now what we have to show? See, we have to show then to show there exists beta inside K star such that f of sigma equals to beta sigma beta inverse sigma inverse beta. That's it. F of sigma equals to beta sigma inverse beta. Sigma inverse beta into beta. That's I have to prove, right? Okay, beta inverse sigma inverse beta. Okay, so you put this to be f of gamma equal to beta inverse, this you put this beta, and sigma beta put gamma to be sigma of beta. That's it. We are done. If your gamma is then your gamma inverse will be what your gamma inverse will be? No, sigma gamma. What is sigma gamma? Sigma gamma is sigma f of sigma. So beta equal to, take beta equal beta inverse, sorry, just a second. You just take beta to be gamma inverse, I guess. That will be enough. That will be fair enough. Or beta to be gamma inverse. Take beta to be gamma inverse. Okay. Or gamma equal to beta inverse. In simple, beta inverse is gamma. Now you put your gamma in case of gamma, you have to put this to be beta inverse, then you will get f of beta inverse. No, sigma will be as it is. No, f of sigma will be sigma of gamma equal to beta inverse into beta inverse. So this will be sigma of beta into beta inverse. That is what we are trying to show. So this implies that F is a member of co-boundary of G, so Galois group with K star. Okay, this implies that this B1, not beta, this B1 Galois group K, Galois group G is exactly same as or isomorphic to Z1 G. This implies that your first cohomology group of G, K star, is 0. This is what we have to show. So done. Proved. This first cohomology group is 0. That is what we have to prove. We have to prove because we just have to basically show that this is same. That means you have to show this is in here, then this you have to show this is in the co-boundary. Okay. Here I have taken one element, I have get it here. So there exists a beta such that this. So this was all about the Hilbert 90 for any cyclic extension. Now for any Galois extension. For any Galois extension it was true. But there is one more there is one more nice form of this Hilbert 90 in terms of norms. What is a norm? Simply saying that if you have K over F be a Galois extension, then norm is a function actually. Norm is a function. Norm is a function from where to where. So if your norm is a function, that means you have a actually if your extension is okay, so this is a function. So how does this norm any element alpha, norm of alpha, we say the n of alpha is actually if your okay, no, not summation, this is product of all those your sigmas are varying over gal group of k over f, and this is sigma of alpha. Okay, this is called norm. This is called a norm if your extension is Galois. Okay, otherwise we don't say. There is some more form of norms in any extension, but we are not going to this. And there is one more called, this is trace of alpha is actually summation of alpha inside Galois group of k over f, and sigma of what is called trace. But we just need norm for this proof, and this will be enough. What we need actually norm. So what is Hilbert 90? One more form for cyclic extension. Hilbert 90 for cyclic extension. Okay, what it says, let G be let K over F be a Galois extension. Let K over F be a cyclic Galois extension with Galois group Kf, and let sigma generates gal k over f cyclic group. So there is a generator, right? So sigma, and if you have a element f, and alpha is in k such that norm of alpha equal to 1, norm of alpha equal to 1, then there exists a beta inside this k such that sigma of beta can be written as if your norm is 1, the norm of this alpha is 1, then this alpha can be written as, then there exists a beta such that this alpha can be written as beta sigma beta inverse. Okay, that's the actual this is for cyclic extension. This is Hilbert 90 for cyclic extensions, and this is a similar kind of proof will follow from here, because your norm is 1. That means because your norm is 1, right? Suppose this is your group, Galois group is generated by this. That means you have some characters. What are the characters? What will be the characters? Proof hint. Similar kind of proof will be here. You have identity sigma square, sigma to the power cube dot sigma to the power n minus 1. This view as a character. If you view this as a character, then the similar kind of follow. What is the norm of alpha equal to 1? What does it mean? Then this alpha, sigma square alpha, all the groups sigma to the power n minus 1 alpha will be 1. So now the similar kind of thing will follow from here. Okay, so similarly you can define this alpha to be something, beta to be something, such that you get at beta. Similar use Dedekind's linear independency of characters. Since the characters are linearly independent, so you can definitely use them. And also use norm of sigma alpha equal to sigma alpha. This is true, right? Because norm of sigma of norm of alpha, sigma of norm of alpha, because sigma of norm of alpha equal to sigma of alpha. I guess this is correct. So you use the same technique where as you have did. So for okay, so you can use the similar kind of argument over here. Now you can use without referring to this cohomology argument also, and this is a little bit tricky one, or that's not a big problem, but you can of course do this is without a cohomology with any kind of cohomology format. So actually if you have any extension with the cyclic extension, with the cyclic, that means that you have Galois group is cyclic. So I think here I have missed norm of sigma of alpha. Sorry, actually this is norm of this. Okay, sorry, norm of sigma of alpha. This is called norm of sigma of alpha equals to norm of alpha. Why this is true? This is nothing but this is nothing but, you can use this also, because you see here what is norm of alpha is the product of alpha in the Galois group sigma of alpha, which is actually alpha sigma of alpha sigma square alpha sigma to the power n minus 1 alpha, right? What is norm of sigma alpha? Product of sigma alpha, where your sigma will vary in the Galois group. This will be what it will be. It will be first will be sigma alpha sigma square alpha sigma to the power n alpha will be there, but this is actually norm of alpha. Sigma to the power n alpha means alpha. This is actually norm of alpha. So this is, you can use the trick. And if you don't want to get any cohomology using cohomology argument, so your norm of sigma alpha equals to norm of alpha. Now you can do the exactly similar argument using the Artin's linearly independence of character. So if since this is 1, so you define your a naught, suppose your a naught to be alpha, you want to a naught to be alpha, a1 to be alpha sigma of alpha, a2 to be alpha sigma of alpha sigma square of alpha. Now we just define this in this way, and you will see that this n minus 1 will be 1, so the all term will be there, and this is the actual norm, and norm is 1. Now you just define some new terminologies, okay, and show that this is true. This Hilbert 90, and also you can use this is very easy to show. Once you have done this cohomology in the format of cohomology, then this is very easy to show. So we don't need to bother about that. So this much is for today. This is called Galois cohomology, and this is called Hilbert 90. This is a very important theorem in Galois theory. Okay, so this is called Hilbert's theorem 90. Okay, so this much is enough, I guess. So thanks for watching. I guess we should okay sorry.